we'll do it pretty soon, like today or tomorrow. I'll try to get them together. We have the solutions, I just didn't post them yet, so it shouldn't be very much work to do it. Did you see the shooting new? Hey Ben, did you see the shooting new? Did you see the news about the shooting? Did you know that guy? Because I know that guy. You knew him? Yeah. The guy with the dreadlocks? From playing the game? Yeah, he played the DLSF all the time. Really? Yeah. I read that it says here they played him. Yeah, we definitely played him in IM a couple of times, yeah. It was weird. It was weird. Yeah, I mean, I just read today. I mean, I just looked at the picture actually, and I was like, oh, I know this guy. CMOS logic dash speed. All right, are we getting going? All right. So, good afternoon, everyone, and welcome to 141. Professor Abai is out of town for a research meeting, so I had to sub in. So hopefully we'll do just fine today. So, all right, so Lab 5 was going on Monday and I think today, this morning, or yesterday, I guess. So that's the last, I think, software lab that we're gonna have. We're gonna have one more hardware lab, but that's about it. So we are gonna start with the project at the end of this week or something like that. I posted homework 5. It's due next Friday, March 14, I guess. So it's a homework that covers this lecture, the past lecture, and the next lecture, I think, too. So there's power and complex gates, basically. That's what it is. And then midterms results are going to be available next Wednesday. We have not started getting the midterms yet because Professor Abai was out of town. So I looked through a few of them, but I can't really say anything at this point. They should be okay. All right, so let's recap last week and what we've done. So we started looking at complex gates in CMOS and how you do design in standard cell, right? So standard cell designs really means you have a subset of logic functions that have been pre-implemented for you by the foundry. And not only you have a subset of logic functions, but also a subset of sizes for each of these logic functions, okay? So you can imagine that if I give you a complete digital, some combinatorial function, there is a large number of ways to implement it. And also, for each of the transistors you put down, you can choose the width and the length. Usually, you would use minimum size for the length, but in principle, you would also not use minimum size. So you can choose the width of the length from a continuous set. This gives you the most freedom, and in fact, it's what's done when you do full custom design. So, for instance, in processors, ALU, and really high-performance blocks, where people really go in and design every transistor individually. But for a lot of applications, this you can imagine has a very a very long design time. And for a lot of applications, you are willing to trade off design time for worse performance or worse power. So in other words, you say, I'm willing to tolerate a slightly lower performance or a slightly higher power, but I don't want to have to design every transistor, okay? And this is where the standard cells come into the picture. So the foundries usually provide you with the library of gates, and there's a set of tools that, given an arbitrary function, map it to this set of gates, which is a finite set, in an optimal way. So now we have gone from a continuous problem, from a continuous optimization problem, to a discrete optimization problem, which is a little easier, but also what is more important is that it takes less time to solve this problem, and you don't have to design the gates. So that's just to remind what the standards were, okay? And so today we're going to look at complex gates and how we really optimize the performance. But before we do that, we're going to go a little bit into the layout of the standard cells. I'm going to go pretty fast. So there's two techniques that I believe were already covered the last lecture, stick diagrams and gate graphs. They are pretty much related. So a stick diagram is a representation of the relative positions of the transistors in a standard cell, in a digital gate, basically. It doesn't have any size information associated with it. All it tells you is just the relative position of the transistors. So for instance, if you look on the left side of this graph, there is an inverter. And so what you can see is that this is the source of the NMOS. This is the drain of the NMOS, which is tied to the drain of the PMOS. And then this is the PMOS, so drain to source. The source of the PMOS is tied to VDD, okay? What this also specifies is that the NMOS and the PMOS have the same orientation. They both have the gate orthogonal to the supply rails. And the gates are connected directly in poly, so there is no gate connection. And this is done to minimize area, really, and avoid the contact. Okay, on the right-hand side, you see an N2 gate. Again, if you think about how an N2 looks like, can we go to the overhead? So if you look at how an N2 looks like, it will look something like this. Are you on the, okay. And so you can imagine this node, this common drain. So there is the sources of the PMOS 1 and 2 are tied to VDD, and here are the sources. And the common drain of the PMOS, it's here. It's tied to the drain of the first NMOS. And then you can see that there is no contact for the junction of these. So these NMOS are really laid out as a multi-finger transistor. I'll get back to this in the next slide. But so this is again done to minimize parasitics at this common node. Okay, so you can really see that this transistor is this transistor, and this guy is this guy. Okay, so this is just a convenient schematic way. If you have to do the layout of a standard cell, you might find this useful to plan what your device positions are before you actually go in and do the layout. So you might want to first, before you start, you open Cadence and you start doing things, you might want to first draw a couple of these stick diagrams to see what's the best configuration of inputs and what's the best routing. Okay? So again, these are exemplifying again. This is a different complex gate. It's C times A plus B. So can we go up? So this will look the pull down as C times A plus B. And then if you remember, the pull up is the dual of the pull down. So these two transistors are connected in parallel in the pull down, so they're going to be connected in series in the pull up. So this is A, this is B. And then these two connections that are in series are going to go into parallel in the pull up. And so this is C, right? So, so as we said, what we want to do for the transistor is try to lay them out as a single multi-finger device, right? But let me skip one slide and explain you what that means. So if you, let's say we have two transistors and we try to lay them out as a multi-finger device, okay? So I can do two of these guys, two of these single finger devices, or a single one of these, okay? As you can imagine, if I have two transistors, each of them has an individual drain and source, okay? So you end up with 4 possible connections for the drain and the source, 2 for each. So what you can do is you can try to combine the two transistors into a single multi-finger device, which is a device that has 2 fingers, which is what is done here, okay? What happens, though, is that now you have only 3 connections. And so these devices need to have either the drain or the source connected in common in order for you to be able to do this, okay? And you can imagine if you try to do with 3 transistors, you end up having, I think you would have 6 connections normally, and for each pair you lose 1, so you end up with 4 possible drain and sources, right? So you need now 2 nodes in common. So in general, there is a non-trivial problem, which is if I give you a logic gate and I tell you that I want to try to use as much as possible multi-finger devices, you need to figure out what's the best ordering of the inputs that minimizes the number of different fingers that you're going to use, right? And so here for this C times A plus B, let's go back to overhead for a second. Actually, let me pull this up. Okay, so this is C times A plus B. And these are 2 possible. Anyway, let's look at the layouts. So if you look at the layouts, A and B naturally share the drain, and you want to share their drain with the source of C, okay? So you have the top transistor. So you have the top transistor here at C, and it shares this node I with the parallel connection of A and B. So A and B share the node, the drain and the source, so they can be laid out as a multi-finger device. But you have the additional constraint of sharing also this node with C, okay? And so let's look at the previous stick diagrams to see what you can do. So in this first case, what you do is you say, I'm going to lay out first, so from the left to the right, I'm going to order first is A, okay? So the source of A, we know is grounded, so that's easy. Then we know that the drain of A has to be tied to the source of C, okay? So if I now decided that the middle gate is the gate of C, this has to be the common node, okay? But now look at what happens. The drain of C has to be tied to the output, and if the next guy over is B, if I draw this as a single transistor, if I basically make a multi-finger device out of these 2, I get that the output is shorted to the drain of B, which is not what I want, right? I will implement a different logic function. So, so in other words, if I choose this ordering, A, C, B, I'm not going to be able to get a single three-finger device for my pull-down network. I'm going to have to use two different device instances. And this means that I have more parasitic capacitance and the area is bigger. So this is undesirable most of the time. So let's look what happens if we instead order them differently and we put A, B, and C. So now what I choose is that, so first of all, because the first two transistors are A and B, I can choose to assign this node either as their common drain or their common source, right? A and B are completely in parallel, so they have both the drain and the source in common. So, however, if I decide this to be the drain of A and B, then this also needs to be the source of C, okay? And again, we end up in a situation where we can get three fingers. So if you work out this, it turns out that the right thing to do is choose this node as the source of A and B and connect it to ground. And then these other two extrema are going to be the drains of B and A. And you need a piece of metal to connect them together too, because otherwise they will not be connected together. And then this also happens to be in common with C. So we know that this is the intermediate node. And therefore, the output has to be the other node that is tied to C, X. So, okay, you can imagine that for this particular example, doing this thing was easy. But it would be nice to come up with a technique that can do it automatically given the schematic. And it turns out such technique exists. It's called the logic graph of a gate. Basically, what you do is for each independent node in the gate, so first of all, you split the gate into a pull-up and a pull-down. And then you fix your attention to either the pull-up or the pull-down. Okay? For each node in the gate, you define a node in a graph. And for each transistor, you define an edge in a graph. Okay? And you end up with a separate graph for the pull-up, which is shown in orange here, and a pull-down. So again, look at this. There is a path, so there is this transistor A is a path from VDD to node J, here it is. Transistor B is a path from node J to X, here it is. And then transistor C ends up being a path from VDD to X, so here it is. And you can do the same thing for the pull-down network. And now there's some mathematical techniques that turns out that you can find what is called the Euler path on this graph, which is a path that visits all nodes, taking every edge only once. And this Euler path, each of these Euler paths correspond to an ordering of the inputs that gives you a multi-finger device. Okay. Of course, for a given gate, it can be that there is no Euler path. Fine, in that case, you can't use a multi-finger device. It's not worth spending your time on trying to do that. There can also be multiple Euler paths associated with the same gate. In each case, all of these are equal. You choose based on some other metric that you're interested in. Okay, so this is not really important. You're probably never going to have to do this in a homework or in a problem, but you know, someone has done this, and therefore there is an automated way to generate the layout, the optimal layout for standard cells. Basically, this is the point. So we don't really need to. So you can do this for more complicated examples. Like this AOI. So this is an AND or invert 22 gate. Again, yeah, you can derive what the Euler paths are and then turn it into a stick diagram. And you can see that for these complex gates, working out to the possibilities by hand is not trivial. And therefore, it's useful to have this automatic tool that spits out this layout without you doing basically almost any work. Okay. So again, these are the techniques that exist, and we don't need to spend too much time on it. All right. So let's summarize. What are the nice properties of CMOS logic that we've seen so far? So I think you've seen a little bit of pass transistor logic, although not really well worked out yet. But you will have seen that pass transistor logic is different from CMOS because it doesn't have full logic levels. You either lose a VT on the plus side or on the minus side if you only use N or PMOS, N or either all N or all P devices, right? Also, the other interesting thing is that this logic is ratio-less, which means that the static characteristic doesn't depend, actually the logic levels, high and low, don't depend on the relative sizing of the NMOS and the PMOS. In other words, think about an inverter that is loaded with the resistor. In that case, VOL depends on the W over L of the transistor and the resistor value. So you can decrease VOL, in other words, get a better noise margin by either increasing the resistor or making the transistor wider, okay? But by doing so, you are either increasing the input capacitance of the device or increasing the output resistance. And in either case, you are degrading speed, okay? In CMOS, what's nice is that you can choose the logic levels independently from the speed, in other words, because you know that no matter how you size the devices, your logic levels are always going to be the same, unless you do something really strange. And therefore, the sizing can be done purely for speed. So you have an additional degree of freedom, basically, as opposed to a ratio device. Okay? Also, this logic is static. It has a low output impedance. A static family means that it is always a low impedance path that connects the output either to ground or to VDD. Okay? This is as opposed to a dynamic logic, where the output is stored on a capacitor, and there is not, at least for either ground or VDD, there is not a clear path. There is not a low impedance path that is connected to. So let me give you an example. Let's go to overhead for a second. One way to make an inverter would be to somehow precharge a capacitor to VDD, and then connect it to with an NMOS gate to ground. This will be the input, and this will be the output, okay? So you can imagine when the input comes and it's low, this inverter doesn't draw any current, and the capacitor stays at VDD, right? So in terms of static characteristic, if my input is low, I'm going to get an output high, okay? But if I now pull the input high, this inverter is going to discharge the capacitor through its drain current, and the output voltage is going to go to 0, okay? So this is a valid logic gate. Of course, this means the fact that you precharge this capacitor means that you need another transistor to do it, okay? And this is typically done with the PMOS. This is called a dynamic logic family, and you will see more in the next lectures about this. But this is typically done for speed, because you can see now, instead of having to enter on an N and a P, as in a CMOS gate, you are entering only on NMOS, okay? So your capacitance is lowered by, roughly speaking, a factor of 3. So because you have lower capacitance, you get basically higher speed for the same current, okay? You might also say, because I have lower capacitance, I have lower power, but that's not really true, because you are adding all these precharged devices, and these are commutating every clock cycle. So it turns out that dynamic is good for speed, but it's not good for power. For power, dynamic is usually worse. So, for instance, dynamic logic is used to do high-speed data paths in processors. All the Intel processors, all the processors you buy, they're all dynamic in their ALU, because their speed matters more than power. But everywhere else, you try to use static as much as possible, because it's better for power, and it's easier to design. Okay? So the other nice thing about CMOS gates is that they have a high input resistance. This is not, these all gates that you build in CMOS have it, regardless of how you do it. And also, they have no static power dissipation, okay? So usually this no static power dissipation is pretty much related to ratioless. Oops. So if a family is ratioless usually, let's say, if a family is ratioed usually, it also has static power dissipation. So this is the case, for example, for pseudo MOS and for like RTL. So this ratioless and the fact that they doesn't have static power dissipation are kind of related, although they're not really the same thing. So, and propagation delay is a function of the load capacitance and the resistance of the transistors. This is always true, I guess. So anyway, if you have questions, you guys have any questions, can I go ahead. We're going to go. This was like almost a complete recap of the last lecture, right? So can I go ahead to the next, the new stuff? Huh? Static CMOS. So what we're going to be looking at is CMOS propagation delay and sizing for speed. Okay. So first of all, if I give you a logic gate, the first question you can ask is, how do I estimate the delay of a complex gate? This is question number one. Once you know how to estimate the delay of a logic gate, you know what parameters it depends upon. Then you have to start thinking about, how am I gonna change these parameters to minimize my delay? Okay. So first we're gonna model the delay, which requires doing actually not very much work. And then after we have modeled the delay, we're going to use this model to size, okay, and to find ways to get higher speed. And we're also going to look at how using this model, we can predict some properties of the delay of a complex logic gate that make it different from an inverter, okay? And these properties are pretty much related to the fact that because when you have a complex logic gate, there are multiple ways to transition from 1 to 0 and from 0 to 1, okay? And this ends up meaning that each of these ways has potentially a different delay. So we'll go over this in the next few minutes, okay? So first of all, let's look at the transistor again. So we assume that our transistor model is the switch model, okay? When the gate voltage is below VT, the switch is open, and so the transistor is off. It still contributes capacitance. So there is a junction capacitor associated with the drain, which we said is the diffusion cap of the N plus drain to the P substrate for an NMOS, or the P plus drain to the N substrate to the N well for a PMOS. There is a similar capacitor associated with the source. And then there is the gate capacitor, which is made of overlaps of gate to drain and of the channel capacitance, of course, okay? The resistance in the on states depends, we said, on the sizing, on the value of VT, and on the value of VDD. In particular, the resistance is inversely proportional to the W over L of the device and to the difference between VDD and VT. Okay? It's actually inversely proportional to the product of these two and to the electromobility. Okay, so now, here's what we do. We take a CMOS logic gate. In this case, this was an AND logic gate, as you can see. There is 2 parallel PMOSs and 2 series NMOS transistors, and we replace it with the switch and some capacitance, okay? Each of these capacitors you would calculate is basically a combination of gate capacitance and drain capacitance. So if I gave you a logic gate with transistor sizes, you will be able to calculate all these C's. And also you will be able to calculate all these R's, okay? So then the question becomes, given these R's and these C's, what's the delay, okay? And so we have seen this. This is an AND. Anyone has an idea what this is? This is an inverter. So there's only one P and one N. The one to the right is NOR, right? There's 2 N in parallel and 2 P in series. So first of all, this is what I was mentioning. The most important property of delay in a complex network is that delay really depends on the input pattern that is applied, okay? And this is very easy to see in this case. Let's take, for example, this NAND gate. And let's consider a low to high transition. And think about what happens when both the inputs are low, okay? So both the switches are open, and both the switches are, both inputs are high. So these 2 switches are closed, and the output is pulled down to ground because these 2 switches are open, right? These are PMOS transistors. So when the inputs are high, these are off, and these 2 conduct. So when you pull up both inputs, when both inputs go low, okay? So A and B were at 1, and now A and B go both together to ground simultaneously, okay? What happens is that both this bottom switch down here, as well as this top switch up here, turn off, okay? But also, both this left switch and both this right switch turn on, okay? And so you can see that the equivalent resistance for going from 0 to 1 in this case is the parallel combination of RP of this switch and RP of this other switch. And therefore it's RP over 2, okay? Now look at what happens if instead of bringing low both inputs, only one input goes low and the other one stays high, okay? So let's say that A goes low and B stays high. So what happens then is that this switch is closed all the time, right? B, we said, is constant at 1. And this switch is open all the time, okay? Still, when you pull down A, this switch is open. So the output doesn't have a path to ground anymore. And this other switch here is closed. So there is now a low impedance path of the output towards the supply. So the output is going to get pulled up towards the supply now, right? So look, why does this happen again? Because these two switches are in series. So it's sufficient to turn off one of them to turn off the series, right? Whereas these two switches are in parallel. So it's enough to turn on one of them to turn on the parallel combination. Okay? But so the point is that because in this transition, only one switch out of two is closed, the resistance that you see is only RP in this case. And so the transition from low to high in this case is roughly twice as low as the transition from low to high in this other case. Because remember, the transition speed is proportional to, the delay is proportional to R times C, right? So if you assume that CL is constant, now your R used to be RP over 2, and now it became R. So it's roughly twice as low. Again, let's look at there is only one possible transition from high to low, which is where both inputs go high. In this case, what happens is that both these switches are closed and both these switches are open. And the resistance you see is 2Rn, okay? So now, what do we do with this information? First of all, you can imagine if a gate has two inputs, there is potentially, I think, 2 to the 2, so 4 different delays, right? That you need to take into account, which is a lot. If a gate has 3 inputs, now you have 8 possible delays in the worst case, which is a lot of numbers to keep in mind. Usually it turns out that what you care about is really the worst case transition, both in the high to low and in the low to high transition. This is because in any case, you're going to design your circuit in such a way that it meets timing in the worst case, right? So you are like throwing away in some sense, some speed, because what you're going to do is you're going to size for worst case, and you're going to have to use the size that guarantees you to settle in the worst case condition, even though this happens only once every, let's say, 10% of the time. But still, you can do anything. It's very hard to do better than this, actually, because unless you know that that particular input pattern is never going to be exercised, which you typically don't know, then you always need to take into account the opportunity that this is going to happen, okay? So you always want, in the end, we're only interested in the critical path, really, in the worst case input pattern. So for this particular gate, the worst case low to high is when only one of A and B goes low. Whereas the worst case high to low transition is easy because there is actually only one, and it's when both inputs go from low to high, okay? So, let me wait a second to go into this. So again, we'll see later that the question that you can ask yourself then is how do I size this gate? So for an inverter, we saw that we would like to size in such a way that the low to high transition has the same delay as the high to low transition, okay? We want to do the same thing for this complex gate case, except that now we have more than one high to low transition and more than one low to high transition. So the next question is like, okay, I want to make the low to high transition the same delay as the high to low transition, right? But what is the right low to high transition and what's the right high to low transition? Because there's multiple of each of them. So it turns out, in general, you try to equalize the worst case low to high transition to the worst case high to low transition. So you take the worst case of both. One is going to be determined by Rn, and one is going to be determined by Rp, right? And then you try to make this Rn equal to this other Rp. And that's how you size it. So for this case, for instance, the worst case pull up as a time constant that is Rp times Cl, and the worst case pull down as a time constant that is 2Rn times Cl, okay? So in this case, you will try to make 2Rn equal to Rp, and in this way, you will have worst case delays equal, okay? And so this will mean that you will make your NMOS roughly the same size as your PMOS, because remember that the mobility of electrons is roughly twice the mobility of volts. Okay, so we'll go over some more examples later, but okay, there is also some other interesting property of complex gates, which is you can imagine that when let's assume that I have one input at 1. Let's say B is fixed at 1, okay? And then what happens in the next cycle is that A was at 0, so the output used to be high. And then A goes to 1. So let's go to overhead, and then I'll draw the transistors again. So what we said we have is that, let's consider this scenario. This is B, this is A, okay? This is the output. And we used to be in this condition where A was low and B was a VDD. And what happens at some point is that A goes high and B stays a VDD, right? So what's going to happen to the gate? The output used to be high, and it's going to go low, right? So this is fine. Let's start putting in some like CL and some C1, okay? So now let's look at another circumstance where we reverse the role of A and B, okay? So in this other case, A was high, and it stays high. So this transistor is always, this node is always at 1. And this node was at 0, and it goes to 1. Okay? So let me ask you, do you think these transitions have the same speed? So again, the first transition is B. The first case is B stays at 1, and A goes from 1 to 0. From 0 to 1, sorry. Okay? This is case 1. And case 2 is A is always at 1, and B goes from 0 to 1. Do you think these have the same speed, or one of them is faster? If one of them is faster, then also which one? Chris, use the microphone.
The second case is faster because the high to low propagation delay is lower than the high to low transition is faster than the low to high.
So these are both high to low transitions, right? Both these transitions are high to low transition. The output always goes from 1 to 0 in this case, because in the end you always have both inputs at 1, and it's just a matter of whether you turn on first the bottom device and then the top device, or you turn on first the top device and then the bottom device. So in this case, it's possible that what you said is correct, that the second transition is faster, but the motivation is not correct. So does anyone else want to answer? You can think a little bit about this. It's not so exotic. Yes?
Well, it seems like depending on which device is on first, you'd have that extra capacitance there.
Okay, this is in the right direction. So let's try to elaborate. Which one is faster then? Okay, so let's consider the case in which this is always at 1, right? So then, because this is always at 1, this capacitor is already discharged at 0. Okay? And now what I do is I turn on this device, this node is immediately at 0, and then I only need to discharge the output capacitor through ID. Okay? In the other case, where this device is on and this device is at 0, this capacitor is actually charged to VDD, because this device is on, this node and this node have roughly the same potential, and because the output we said is at 1, this node is at 1. So because this node is at 1 and these nodes have the same potential, this node is also at 1, right? So what happens then is that when I turn on the bottom device, first I need to turn to discharge this old capacitor, and then I also need to pull the charge of this other capacitor, okay? So roughly speaking, I'm going to be looking at a transition that is proportionally slower. In other words, in one case, I'm discharging C1 plus CL, and in the other case, I'm discharging CL. So if C1 is the same size as CL, these transitions will be roughly twice as low as the other. But in reality, C1 is actually smaller than CL usually, and therefore, it's not that bad of the difference. But still, there is a significant difference. So is anyone clear with what's happening again? So this is what, again, we are looking at. A goes from 0 to 1 in one case. In the other case, it's B that goes from 0 to 1. Okay? And all we are saying is that the transition in which A goes from 0 to 1 is faster than the transition in which B goes from 0 to 1. Okay? And so this is important design implications, because you can imagine if your critical path goes through this gate, you want to goes through one of the inputs of this gate, you want that input to be the top one and not the bottom one. I will go back to this again in a little bit. All right, so sizing. Let's go back in detail at this and try to make a couple of examples. Okay? How do we size the transistors for delay in a complex gate? We already said that a couple of slides ago. Let's look at, again, one specific example. And we'll do NAND and NOR. Let's go to overhead, please. Okay. So first we do a NAND gate, okay? So the goal of our exercise, in this case, is to find the sizes of all these devices, okay? Let's call this M1, M2, M3, M4, in such a way that the delay of this gate matches the delay for the same output capacitance, right? Matches the delay of this inverter. And we are gonna, which has the same output capacitance, is a unit inverter. Let's assume that we have some reference inverter, okay? And then the size of the NMOS in the inverter is 1, and the PMOS in the inverter is size 2, okay? So what we want to do now is we want to find the sizes relative to this inverter. So in other words, how much bigger than, if this is your unit element, how big M1 has to be and how big M2 has to be in order for the delay to be the same. Also, we want the worst case low to high transition to be the same as the worst case high to low transition for this complex gate. Okay? So how do we do that? Does anyone have an idea of how this is done? I already went through it very quickly in the last slide, so maybe you should think about it for a couple of minutes, and then I'll go. Think about it for a minute or so, and then I'll give you the solution to this. Or if anyone wants to give the solution himself, then just pick up the microphone and speak up. So just for your convenience, this is an AND gate, so it's equivalent to the gate on the left, the gate that I'm highlighting right now. This is the resistor model of the NAND gate, okay? For these first times, it's probably useful for you to think about it in terms of resistors, but you will see as you go on and on, you won't need to draw the resistors all the time. You will just look at the gate and you will know by inspection what the right sizing is. Or at least you are expected to be able to do so by the end of the class. Okay, anyone has an idea of how you would size this gate? All right, so we said that the delay has to be the same, right, in the worst case. And we said that in the worst case, the pull down on resistance is the series of these two resistors. Because remember, if we go back to the slide, remember, in the worst case pull down, both these transistors, both these switches are closed, and so we are seeing 2Rn, okay? So we want, so if this guy has Rn, here we are going to see 2Rn in the worst case. So what we do is we do Rn of these devices to the left, half of Rn of the inverter, okay? Which means that we make their width twice as large as the width of the inverter, okay? There's two transistors in series. The worst case is when both are on. Therefore, the worst case resistance is twice the resistance of each of them. Because we want the total resistance to be constant, then we just decrease each of these resistors' value by the same amount, and we make it half each, right? And so this is 2x now, and this is 2x. Now let's look at the PMOS devices. So in the PMOS case, the pull-up is only one transistor, and we again want the same driving strength for the pull-up that we wanted for the pull-down, right? So in the inverter case, the pull-up was one transistor with size 2, and here again we have only one transistor. So the size of this transistor is going to be the same. Because remember, in the worst case, only one transistor pulls up the output in this gate, okay? And this is the key. So what this means is that there is going to be one transition. So we're going to size both these PMOS to be 2x, right? So that in case A goes low and B stays high, or A stays high and B goes low, we are going to have the same pull-up strength as a standard inverter. But there is still going to be the case where both A and B go down at the same time. And in this case, we're going to have a pull-up strength that is both of these devices. And therefore, it's going to be twice as strong as the inverter. And therefore, in this particular fortunate condition, we are going to have a delay which is roughly half that of our reference inverter. However, this is not useful because we don't know if we get the worst case delay or the best case delay. And therefore, we always need to design for the worst case delay. Okay? So this was NAND. Let's try to do NOR. NOR, if you go back to the slides for a second, is the slide. Can we go back to the slide real quick? Okay, NOR is this gate, okay? So let's draw the NOR in circuits. So if you look at this NOR gate and you compare to the previous NAND, you will see that this NOR is actually the dual of the NAND gate. So in other words, the NAND gate has two series NMOS and two parallel PMOS devices. And the NOR gate has two parallel NMOS and two series PMOS devices. And the output is taken here now. So this is CL. Okay? So again, let's look at what's the worst case transition now. For the high to low case, the worst case transition happens when B is stuck at 0, let's say, and A goes from 0 to 1. Okay? Or equivalently, A is fixed at 0, and B goes from 0 to 1. In this case, only one of these two pull-down devices is going to be active, okay? And therefore, the pull-down strength is going to be the same as the pull-down strength of a single device. Or in other words, the equivalent resistance of the pull-down network is going to be just the Rn of the MOS transistor. If we, again, try to equalize this to our reference inverter, we end up with this is 1x and this is 1x, right? So that they have the same strength. Now, let's look at the pull-up network. So this gate, as much as the NAND only pulls down when both inputs are high, this gate pulls up only when both inputs are low, okay? So in this case, there is only one value of T low to high. And this value happens when both inputs are, or either input is, well, basically when something happens and both inputs end up being at 0, okay? In this case, the pull-up strength is given by 2 RP, okay? And we want 2 RP to be equal to the pull-up resistance of our equivalent inverter, which was for a 2x size inverter, okay? And therefore, we need to make each of these devices, again, twice as wide as it was in the inverter case. And therefore, each of these devices ends up being twice times 2, so 4x. Okay, so we can already compare the NAND and the NOR gates from a very interesting point of view, and which is the following. Okay, so I think you all know, so it should be a known fact that if I give you an arbitrary combinational function and I only give you AND and NAND gates, you can always, and in inverters, you can always implement it, right? So, you know, and the same is true also for NOR gates. So if I give you NORs only and inverters, or NANDs only and inverters, you can always implement any arbitrary logic function. But, so the interesting thing is that which one would you choose in practice? Well, you can see that for the same delay, the input capacitance of a NOR is the input is like it has this 4x PMOS and this 1x NMOS, right? So the input capacitance of the NOR gate is 5x, okay? Whereas the NAND gate has a 2x NMOS and a 2x PMOS, and therefore the input capacitance now is 4x, where x is just the input capacitance of the unit inverter of the unit transistor, right? And remember, the inverter has a capacitance of 1x for the NMOS and 2x for the PMOS, and so the total capacitance is 3x. And all these three gates, they have the same driving current ability. So they have the same equivalent worst case on resistance, okay? And what this tells you is that the inverter is the best, but then if you have to choose between NAND gates and NOR gates, you always want to use NAND gates because they have lower capacitance. In other words, they go faster for the same power, or they dissipate less power for the same speed, okay? So this is the reason why NAND gates are a little bit more popular than NOR gates if you look at arrays and programmable logic, for instance. All right, so we can do a little bit of more complex exercise. Let's go to slides on this complex gate, which is D plus A times B plus C bar, okay? So I would like to take the opportunity to remark like a common property of all the CMOS gates that at least I know. All the CMOS gates that I know are all inverting naturally. If you want to do a non-inverting gate, you need to put an inverter somewhere. And this is because, I mean, it's very easy to do inverting gates, right? Because the transistor, naturally, if you pull up the gate of an NMOS, the NMOS pulls current down and pulls the output down. So this is already something like, you know, I have a high input and I get a low output. So it's already an inversion. So usually it's simpler to build inverting functions than to build non-inverting functions. This is kind of counterintuitive, at least for me. Because you will think that to invert something, first you do it and then you take the complement. It turns out that's not really what happens. Okay. So if you go through the same type of analysis, let's look at the pull down now. Okay. There's two parts to the pull down, and there is going to be a worst case delay for the left hand side path, this one, and a worst case delay for the right hand side path. Okay. Now, because there is two worst case delays, we not only want them to be equal to that of a reference inverter, but we also want them to be equal between themselves. Okay. So you can discharge either by pulling up D here, or by pulling up A and one of B or C. And we want the speed of these two to be the same in the worst case of each branch. Okay. So the branch that has D only. So these things are important. So if you have questions, you should ask. So the case of D only is easy. There is only one transistor, so it can only be 1x, right? So let's look at the right. The worst case is when A is on. A has to be on for the network to pull down. So there's no way around that. This is the only. If you want this branch to be to pull down, A has to be on. Okay. And then one of B and C. So therefore, in the worst case, how many transistors are there between the output and ground? Does anyone want to guess? Who's for one? Raise your hand if you think there is one transistor in the worst case. Who's for two? Okay, pretty much everyone should be for two because there is two. So either A or one of either A or B and B or A and C, right? So therefore, we size all of these A, B, and C to be 2x, so that the resistance in the worst case is the same as is 1, right? And that's what we do. 2, 2, 2. Let's look at the pull up now. So again, for the pull up, we need to turn on D to hope to pull up something, and then we can either have A active or B and C, right? So just from these, we would expect the size of A to be roughly half of the size of each B and C. Because in the worst case, we can either pull up through D and A, or D and the series of B and C. And because these two paths have to have the same delay, this means that the series of B and C have to have the same resistance as A only. And therefore, okay, we can go into the analysis. We see that A is size 3x and D is size 6x, and then C and B are twice as big as A. Okay. Okay, so so far we have assumed that these resistors really stack. When you stack two NMOSes, the equivalent resistance is really twice the equivalent resistance of a single MOS device. This turns out not to be really the case because there is short channel effects. And if you take into account short channel effects, basically it turns out that the stack of two devices acts as a transistor which has longer channel length, and therefore it's less velocity saturated than a transistor of, let's say, half the width and the same channel length. So this is a little bit of a tricky thing, okay? So what I'm saying is that if you stack two devices which have the same W, so basically what we assume so far, let's go to overhead for a second. So what we assume so far is that if I give you this guy as W over L, right? And this guy as W over L. Basically, all we assumed is that this is equivalent to a single device that has W over 2 width and length L, okay? Whereas physically, what happens is that the channels of these transistors are in series, really. And so this looks more like a single device, which has a width of W still, but a length of 2L. So here's the subtlety, right? We are realizing a W over L ratio that is half of the original one in either case, okay? So therefore, if these transistors were quadratic, doing a transistor which has W over 2 over L or W over 2L will give you the same exact IV characteristics, right? And therefore the same delay. But because these transistors have short channel effects, it turns out that from the point of view of on current, a transistor that has W over 2L is slightly better than a transistor that has W over 2 over L. And this is because when you are using this as a pull down, so this node is a VDD, and this node is a VDD, okay? The VDS of this device is VDD. And so the average electric field, if the device has 2L, is VDD over 2L, right? Whereas in this case, the average electric field is VDD over L. So you can see from this that this guy operates as a higher electric field than the guy on the left. And therefore, it's going to be more velocity saturated than the guy on the left, okay? So because we know that velocity saturation degrades the on current, we know that the guy on the right is slower than the guy on the left. Okay, does anyone follow this? Okay, so because so far we assume that when we stack two devices, we are going to have the same resistance. We're going to have to make each of them twice as big. We were basically assuming that these two devices stacked behaved as this guy, right? But we just concluded that not only these two devices stacked behave more like this guy to the left and not the guy to the right. And because this guy to the left has more current than the guy to the right, the optimal scaling will not be 2 in reality, but will be something like more between 1.5 and 1.7, let's say. Okay? And if you look at real standard cells, that's what is done typically. But we'll go back on this in the homeworks in the future. So we'll have a chance to look at this from a simulation standpoint and look at what's the difference really between these two devices. All right? So there is another interesting question is, how do we model, again, the delay of a complex gate? So far, what we said is that, let's stay with overhead. So far what we said is that the delay is still going to be given by the equivalent series resistance, let's say, of the pull down times the load capacitance, right? So let's make this thought exercise where we take devices of a fixed size, W over L, and we start making a more and more complex gate, right? So we start from a gate that has an inverter. I'm going to draw the pull down, but you can imagine the pull up, right? This is W over L. Then I'm going to make a 2 NAND, so 2 devices stacked. Each of these is still W over L. I'm not trying to keep the delay constant. I'm just trying to stack more devices. And I'm fixing also the load capacitance, so the load capacitance is constant. Then I try to do 3 devices. Then I try to do, 4 devices. Okay, so from the analysis that we have done so far, if I was to plot the delay now, the high to low delay of these networks in the worst case, as a function of the number of inputs, the first one would have Rn times CL, right? The second one would have 2Rn times CL. The third one would have 3Rn times CL. And the fourth one will be 4Rn times CL. And the fifth one, the sixth one, the seventh one, there will be 5, 6, 7 Rn times CL. Okay? In other words, if I was to plot, according to this model, the TP high to low as a function of the number of inputs, which is also called the fan-in of the gate, this will be a linear function. Okay? However, if you try and do this exercise and you simulate in SPICE, you don't find a linear function. You find something that looks like, it goes a lot faster. It's more a quadratic function. Okay? So why is that? The reason is these parasitic capacitors here that you add. So as you add more stages, you can imagine that in order to discharge the output, let's go back. Well, let's stay on the slides. It's fine. In order to discharge the output, not only you have to discharge this CL, but you're also discharging C3 and then rippling through C2 and then rippling through C1, right? So these capacitors end up having an impact on the output, on the delay. In particular, what you can do is the following. Let's go to overhead now. If I give you this long chain of transistors, you can replace each of them with its RC model. So there is CL here, right? So the first transistor gives me an R and a C. Then I go into the second transistor. That gives me another R and another C. Then I go into the third transistor. That gives me another R and another C. Then I go into the fourth transistor. And this gives me another R and another C. And then there's 5 of them, so there is a fifth transistor. This gives me another R and another C. And this C is grounded, so it doesn't matter. Now, this is a distributed RC network. And in homework 1, we've seen how to solve these. In homework 2, I guess, we've seen how to solve these using open circuit time constants or solving a fifth order differential equation, which is not really practical. I would not recommend doing that. So there is also a more digital specific way of doing this, which is called Elmore delay model. And Elmore delay model, you will see, is very much related to open circuit time constants. And what that tells you is that to calculate the delay of this node going from 1 to 0 through this network, what you have to do is you want to consider the sum of multiple time constants again. And these are obtained as follows. For each capacitor, you open circuit all the other capacitors, and then you take a first time constant, right? So you walk from the output back towards the input. In this case, you walk from here towards, ground. So you take this first capacitor, you ignore all other capacitors, you look what's the equivalent resistance in, which is 1, 2, 3, 5R. And you say, okay, my first tau is 5R CL, okay? Then I look at this first parasitic capacitor, C1. I ignore all other capacitors, and I look at what's the equivalent resistance to ground. So now, looking upwards, this is an open circuit, so this doesn't matter. You can only look downwards, right? And so in this case, you will have tau 2 equal to 4R times C1. And then you will do the same for tau 3, for this other capacitor. Again, looking upwards, you see open, so it doesn't matter. Looking down, you see 3R. So we can call tau 3 equal to 3R C2. And so on. Tau 4 is going to be 2R C3. And tau 5 is going to be R C4. Okay? And what Elmore delay tells me is that the equivalent tau of the delay is the sum of all these. Okay? So the tau equivalent is tau 1 plus tau 2 plus blah, 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 tau 5. Okay? So now, what's the impact of this equation? So this is usually a good approximation of what the delay is. And if you are familiar with open circuit time constants, you will see that it's kind of similar. So what's the implication, okay? So now, in order to get the implication, let's assume that CL is equal to C1, is equal to C2, to C3, to C4, okay? These capacitors are all equal. And let's try to compute the sum of tau I when all capacitors are equal. This is going to be equal to 5RC plus 4RC plus 3RC plus 2RC plus RC. In other words, it's also equal to RC times sum from I equal to 1 to n of i's, okay? And we know that this is equal to RC times n squared times, n times n plus 1 over 2, right? In other words, what we found is that if all capacitors were equal, we would have a quadratic dependence of the TP on the number of inputs, okay? And this indeed is what you observe in simulation, okay? It's a little smoothed out by the fact that usually CL is bigger than all these CIs. But indeed, okay, so what you can observe is that if all the CIs were zeros, the only term that would remain would be the term with the CL, right? So you will get linear delay in the number of inputs. If all these C's were 0, if all these other C's are 0, then you only get this term, okay? So in other words, if all these C's are all the parasitics, so if you don't have parasitics of the transistors, you only get the first term, which tells you linear delay in the number of inputs. If CL and all the parasitics were of the same value, you will get this analysis, and this will be quadratic in the number of inputs. In reality, the C1s and C2, C3, C4, they're not 0, but they're not as big as CL, okay? So you don't get linear, you get more than linear, but you get less than quadratic. You get something in between. It depends on the specific technology, okay? So let's go back to the slide. So, okay, and as I said, we see that this result is quadratic due to the increase in resistance and capacitance. And therefore, we also know that the TP, of course, is linear in the fan-out, which means if you increase the load capacitance, then the delay increases linearly. That's fine. Okay, so at this point, we have gone through all this analysis of how the delay depends on the size of the network, how to size the NMOS, the PMOS. What can we do for improving this, to improve the speed, okay? So the first thing that we can do has very much to do with this Elmore delay that I just mentioned, okay? And we have seen that if you think about it, okay, how the Elmore delay expansion is derived, you multiply this CL with the sum of the resistance of this device plus the resistance of this device plus the resistance of this device plus the resistance of this device, right? Then you take C3 and you multiply by the resistance of this device times plus the resistance of this device plus the resistance of this device. Then you take C2 and you multiply times the resistance of this device plus the resistance of this device. And eventually C1 is also multiplied by the resistance of this device. So now I could go back and ask you, in how many terms does the resistance of the first device enter? Anyone wants to answer this? How many terms, if you were to write down all these RCs that I just showed you, in how many of them you will see the equivalent resistance of the top MOS? Okay? Does anyone want to answer? Go ahead.
Just one.
Okay, just the first one, right? And the second one would only appear in 2, and the third one would only appear in 3, and the fourth one will only appear in 4, okay? Would appear in all 4. So what this means is that if you try to make all these resistors the same, you are basically wasting capacitance on these nodes, right? Because you are generating a high capacitance node to make this transistor the same resistance as this. But in the end, the delay benefit that you get is 4 times smaller than you get from this guy. So you will want to do something more clever, which is you try to make this device narrower than this device. And then this device yet narrower than this device. And then this device is the biggest of all, right? So you kind of taper this RC network to minimize delay. It turns out this is a really good idea in theory. In practice, it doesn't work as well because what happens is that if these devices have different sizes, you can't really share the junctions. So your layout gets more complicated. Because you can't share the junctions, you add more parasitics. So you did all these things to get, smaller delay, but you are adding capacitance, which also increases the delay. Also, the area is bigger because, again, you can't share as much. So it turns out this gives some, 20% improvement. But, it might look a little better on paper than it does look once you actually implement it, okay? Another thing that you want to do, which is much more effective, is transistor ordering, okay? So now, let's assume that your delay goes through these 3 input gates, okay? And you want to minimize the delay. Also, you know that there is a particular input that sets your delay. In other words, for instance, you know that these in 2 and in 3 are always going to arrive earlier than in 1, right? This is because of how your circuit is built. For instance, maybe this in 1 goes through 10 inverters before going to M1. And this in 2 and in 3 maybe go through only 1 inverter, okay? So when the gate operates, in 1, you know that in 1, in 2, and in 3 are never going to arrive at the same time. But there's always one of them that is going to arrive first, right? So then what you want to avoid doing is putting the guy that arrives last at the bottom. Because we already derived before that this transition is the slowest, right? So what you want to do instead is you want to put the guy that arrives last closest to the output. Because in this case, this C2 and C1 are already discharged. And this transition is the fastest. In this way, the overall transition speed is maximized, right? So this is actually, this is actually something that you have, this is like almost comes at no cost, right? You might do your routing a little more complicated, but this is something you really have to do all the time. It's always a good idea to do reordering and to think about what inputs arrive first and what inputs arrive later to the gate, and take advantage of that in your input distribution, when you assign the inputs. Okay, so this is something that is really something you have to do. The other thing you can think about is, how do I choose my logic structure, okay? Again, you can try to do, if you have a 6-input logic function, you can try to do it with the 6-input logic gate. Is this 7-input even? It's 8 inputs, even better. So you can try to do it with an 8-input logic gate, or you can try to break it up in multiple stages, right? And so here you can see an interesting analysis, because if the delay was linear in the fan-in, you would always do this big 8-input logic gate, right? More or less. But actually, sorry, let me take this back. It's not true that if the delay was linear in the fan-in, you would always do a complex logic gate. But anyway, it's even more true that because this 8-input logic gate is not twice as low as a 4-input logic gate, that you don't want to do this. This is very slow, okay? Usually, you're much better off for speed by breaking the function into a multiplicity of gates with smaller fan-in. So you can see that because you use multiple stages, you accumulate a higher number of delays, right? So in this case, you only have the delay of this 8-input NAND plus the delay of an inverter. And in this case, you have the delay of a 2-input NAND, the delay of a 2-input NOR, the delay of a 2-input NAND again, and then the delay of an inverter. But because this delay of this 8-input gate is so big, you're most likely better off by using more stages, each of which has a much smaller delay, than by using a single stage, which has a large delay, okay? And this is just because, again, the number of stages grows slower than the delay if you increase the number of inputs, right? Otherwise, this will not be true. Okay, the other thing you might want to do is you might want to, again, we look at buffer sizing and how to choose an optimal buffer scaling strategy to minimize delay. Even if you are not doing strictly a buffer, but you're doing a gate, it might be better, instead of trying to drive a big cap directly with the gate, to try to put some buffering in between, right? And so this is also something you have to do, actually. It's not really an option. If you have a big capacitor and you try to drive it directly with your gate, you end up with either a very slow transition on this node or a huge capacitance at these inputs, and neither of them works really well. So what you want to do instead is you want to try to drive with your gate some inverter, and then with this inverter, some other inverter, and maybe you need more than 2 inverters. Maybe you need 3 or 4, right? You can calculate what's the optimal number of inverters in general. So that each of these inverters has a progressively smaller input capacitance, and so the input capacitance of this guy doesn't end up being big, and yet you get a good propagation delay here. So the last thing you can try to do is you can try to reduce the voltage swing at the output of the gate. So again, let me remind you. We have seen so far that when you want to discharge a node, for instance, right, you have a capacitor C, and you charge it at VDD. You want to discharge it to VDD over 2 or to ground, and you do it through a current source ID SAT, right? So what you can say is that, how do I reduce delay? Well, instead of discharging this capacitor from VDD to VDD over 2, I will discharge it to VDD over 10. So, sorry, to VDD times 0.75, right? So 3/4 of VDD. So instead of going half capacitance, I'm going to go, instead of going full rail, I'm going to go to half the rail. So of course this works well for one gate. If you have 2 gates, it works a little less well, because now the next gate operates with the lower input voltage, and therefore it's lower. But there are particular cases. Can we go back to slides? So there are special cases where this ends up being a win. And one of them is in memories, okay? So what you typically end up doing is you add some gate that is different from the others, and it has a particular property of being very fast, even with small inputs. And in memories, this is done, and this particular gate is called the sense amplifier. And so again, this technique is not very general. The most general things are really reordering the inputs and restructuring the logic. These are the most general things you can do to make things faster. But then there is cases where this applies to. Okay? And this is pretty much it for today. So we are like 2 minutes early, so almost perfectly on time. Okay? So next lectures are going to be logical effort and speed again. Yep. Yes. Yeah. They had velocity saturation 0.3 for the N and 0.6 for the P, right? Yeah, I think so. If you think about it in terms of critical field, the critical field, which means the field at which the velocity, the mobility is degraded to half, is about 5 volt per micron. Okay. So 5 volt per micron means on a 0.1 micron device, half a volt. So now what we are looking at in this case would be 3 volts per micron.